Okay, class, welcome back. Let's get it started. In previous class, we discussed about the ocean system, what defines the ocean system, what's the component, and what's the key features of the ocean systems. And I handed out a paper or equivalent book chapter number 3 and 4. The title is Practical Ship Design, written by Watson, and I strongly recommend you to skim through it because it summarizes the overall process, the very basic of overall process, how we can design a ship even though we don't have anything on hand. So it covers how we can estimate something based on the very limited information, and how we can proceed to the next step, and by this process, how we can accumulate the kind of guessed information. However, once this guessed information is growing larger and larger, we can have more information, and we can check those information with each other and make it kind of our stepping stone to the next iteration step. So I show the design spiral. So if you go again and again and again and again, and eventually you will get into one sweet spot, which we call it your final design. However, it is not automatically done. As I mentioned in the previous class, it's a spiral thing, basically, but it does not necessarily mean it will converge automatically. Sometimes while you do iteration, it could diverge to somewhere else, which is bad. So you need some kind of decision. If your design progress showing some kind of symptom of divergence, then you have to check. Maybe it's because your initial guess is totally wrong, or maybe it's because of your calculation or formula you've used are not effectively model your problem itself. Anyway, that's the details of the thing. And I sent it out today's lecture note by email this morning, so maybe some of you don't even get the information yet. However, in today's class, we will briefly discuss about the overview of the marine design. And how many of you read through the Practical Ship Design chapter 3 and 4? Anyone? Okay, good one, Simon. Yep. Practical Ship Design chapter 3 and 4. If your background is naval architecture, then you don't have to read it everything. But if your background is not of that, then I strongly recommend you to read it and understand it everything. Okay, first thing first. I will continue the lecture assuming that you are familiar with those practical ship design approach. As I mentioned in previous classes, nothing is done alone nowadays. Group of 10s, group of 20, 30, 100 will work on the same project, while as long as you work in this ocean systems engineering field, naval architecture and offshore engineering field, nobody can single-handedly build a ship, build offshore plant, build a submarine and the like. You got to work with someone else, especially with same background, but essentially there should be a divergence of your background. Think of a design team of offshore plant. What if all the members are just neighbor architect without any chemical engineer? What if there is no electronic engineer? What if there is no structural engineer? It will be disastrous. So your design team basically consists of your manager, consists of peoples, not necessarily engineers, peoples of a variety of fields, and you got to know about the language. I mean language, not English or Korean. You may have confronted some kind of difficulties in communication while you talk with computer scientist or chemical engineer or MBA or some human resource people, because if you say something, it is totally different by their means. I have a similar experience. While I was working as a postdoctoral researcher at the University of Michigan, I was kind of in charge of some development team. My job is to get everybody work together to develop some kind of early stage surface worship design optimization tool. I had to work with Navy officer who are our sponsor, who gave us job, and I have 2 PhD students, naval architecture department, and I have 1 computer scientist just for the hire, because we got to do a lot of computer programming. So we thought it is not that effective. We do the programming. We naval architect or marine engineer. So the problem is it took me about 6 months to truly communicate with this programmer. He doesn't know anything about forces, moments, and balances, but our naval architects doesn't know about the hash table, something like that. But in order to work together to complete a project, we got to think about the collaboration. And this collaboration actually heavily affects your design process. For example, if there is one computer scientist and 1 mechanical engineer, and let's assume this mechanical engineer is the boss of this design team. As a manager of design project, this mechanical engineer will define the schedule, work steps, the goal of our project. But in other sense, these goals, subtasks, and their hierarchical interrelationship and their schedules could mean just garbage to computer scientists. Okay? So, for that one, in later courses in our in later classes in our courses, we will briefly touch about how we can build a better team by identifying our inner self, your type, the environment you can perform better, and the like. And I call it team dynamics. And books I mentioned, team players and teamworks are truly about this topic. Okay, second, this is the suggested reading to overview the process of the basic marine design and how these design processes are defined or suggested and innovated. The first one is written by Bennett and Lamb, Concurrent Engineering, Application and Implementation for U.S. Shipbuilding. It is quite old one, written in 1996. But this covers the key aspect of the effort how this U.S. shipbuilding industry are trying to minimize their overall construction and design time of their ships. Their key idea was concurrent engineering. As the word concurrent means, they try to do concurrently. I mean, concurrent means doing it at the same time. For example, if task A should be done before task B, I mean, logically, concurrent engineering is doing it at the same time. How? Logically, it is not possible. However, practically, it is possible. Korean shipbuilders are very good at their production, and they just do it, even though they are not familiar with this concurrent engineering. For example, logically, you got to have all the details of drawings before you begin to cut the steel, right? That's a logical step. But in Korean shipbuilders, shipyard, they don't do like that. They begin to cut the steel even though the design is not yet finalized. How this is possible? Well, you may read the paper, and I will distribute this paper through our TA. The second paper is written by Keen and Tibbetts. The title is Revolution in Warship Design, Navy Industry Integrated Product Teams. The key word in this paper is the integrated product team. And someone prepared to quote, and you will hear this term a lot if you go into the industry. The basic idea is that inside of this team, for example, design, I don't know, maybe outfitting, some quality assurance and the like, but in design department, even though they have different background, everyone are designers. Their job is to design something. But to make this overall project, it is not enough. Because in your design team, all your brain is just focused on your design task. But if you go a little bit higher, design is not everything. You have to think about the production. At the same time, design and other things. So this IPT idea came from automobile industry. So the key idea is to build a team. Some from design department, some from purchasing department, some from manufacturing department, and make a team and give them some kind of authority to make a decision. Okay? Can you guess what is the key benefit of this IPT? Anyone? Yeah, Simon?
Because I think it's a globalized answer. It's not just the point of view. Different places to identify and consensus between all the different parties.
Okay. Yeah. Yeah. Sometimes your own task, for example, design a suspension system in Hyundai Motor Company, can affect any other things. If your shape of suspension system changes, it may changes your chassis shape or weight balance, or by changing this chassis shape, you may have to change the CFD analysis and the like. Or you should think about, is this just enough, or is this just possible to produce 10,000 of the same unit in a given time, or and the like. So nowadays everything is very complex, and you need a lot of this kind of IPT. There are several ways to achieve this benefit. The first thing is build a team out of many departments. And the second thing is build your organization, change your organization. Somebody call it a matrix organization or task force organization, but these are related to this one. Okay, let's think about our design, and because this is the earlier phase of our overall classes, we got to think about the size, the complexity of our job. Offshore platform or field, that is the approximated cost. This information is quite old, so it may not project the real value, but relative information, you can compare the relative cost between these things. Offshore platform, military ship, warship, commercial ship, custom motor yacht, it's a kind of luxury yacht, sailing yacht, not so luxury yacht, and ski boat. Ski boat is the thing like motorcycle on water, water jet, water ski, something like that. And it is categorized by the system complexity. Ski boat are quite simple ocean system. But the other extreme is the offshore platform or offshore field. It's about $4 billion and down to $10,000. Okay, in Korean currency, ski boat cost about 1,000,000 won. It's a little less than your compact car, maybe less than that, but I don't know. But $4 billion, can you imagine how large this amount is? To me, it's just a number. As I mentioned before, we got to collaborate, but we do prefer the functional organization. Okay? Structural engineer gather together in a structural engineering department, CFD engineer gather together in CFD department, and the like, because they wanted to gather the same engineers with same background to earn the synergy among them. You can grow the domain-specific expert information very fast in doing so. However, you may lose something, very important thing. And in previous two papers, they call it over the fence. Because everything is sequential, if you do something here and you gather all the report and result and give it to the next department. Okay? Think of this knowledge you share while you design something. And it is not that easy to grab down all this information into a written form. it is really, really important, and it is true. It is really, really important to have the document, report, and all the material systematically summarized in the forms of written material, but sending it over the fence, inherently it loses some of your information, which could be critical. Okay? Traditional ship design has been sequential in older times, but nowadays it changes to concurrent design. Because why? Any idea? To do it concurrently, you need more energy. I mean, you think more, you have to plan more, you have to implement some kind of very complex computer system, and all other effort. You need extra effort. But why do you do that?
I can explain the typical example for the official system development. And for example, at the conceptual or the preliminary design phase, the naval architecture should determine the design node for the official structure. But in early times, for example, 20 or 30 years ago, at the time the structure of the platform system was determined based on the deterministic design node. For example, the hydraulic dynamic node or the wave node. But at this time, the official system designed based on the reliability or the risk-based approach. Therefore, for example, the risk, the fire and the explosion risk analysis is a mandatory analysis study for the determine the required structure design node. But there is some very critical difficulty to determine the structure design node based on the risk-based study. For example, at early time for the project, the labor architecture and another management should determine how many steps should be required for this project. But the explosion analysis usually conducting based on the detailed 3D design layout. As you know, at the early stage, this 3D layout is not determined. Therefore, the explosion analysis expert or engineer should be the guess or the assume the future 3D layout at the early stage because they should give some initial value or the preliminary value to the naval architecture engineer to determine the feasible structure design basis. This is, in my opinion, this is a typical example, but difficult for the current.
Yeah, thank you. Yeah, you're right. Let me summarize it like that. Nowadays, we have many cars on the market. But if your product is Pony 2, can you survive? I don't think so. Nobody will purchase it. Okay? Even though the cost is very low. Okay? Nowadays, there are many other expectations about your product. A long time ago, those terminology or concept doesn't exist. For example, at old times, there is no airbag system. There is no collision analysis at all in design phase. There is no, ABS brake system or, stabilization, VDC or something like that. They don't exist in a longer time, but nowadays we have it. Why? Because that's the market. Company does not dictate the market. We have to satisfy the market, and the satisfaction level increased a lot. That's a very nice example, and thank you for. The other thing is, it's about also the survival of your company. About 5 years ago, 10,000 TEU container ships are built in about 26 months or so, if I remember correctly. Nowadays, they built in about 22 months or so. I'm not sure about this number. Korean shipyards doing it faster because they wanted to survive. Your company, if you own it, or have to have some kind of competence, competitive edges. It could be cost, same product, same quality, but cost less. Then you have some kind of competitive edges. Or same price, but the quality is higher, then you have competitive edges. Especially in ocean systems engineering field, I said it is make-to-order system. It is not Sonata. You can produce tens of millions of the same thing and put on your warehouse and give it. You cannot sell it to the customer waiting for it. You got the order from the customer, ship owner, and you do the design, construction, and delivers it. The time, think about $4 billion hanging, doing nothing. I mean, in the shoes of the ship owner, you have $4 billion invested it. Okay, think of the interest. So 1 month less or 1 month fast, which makes a big differences. Okay, because of that, shorter delivery time is one of the key competitive edges in shipbuilding industry and ocean systems engineering. Okay, because of that, they do the concurrent engineering, and if they don't do that, they cannot survive at all, because there are many competitors doing very well. Okay. Okay, the second line explains those things. Partially driven, supported by basically competitive bidding process. This process is not well covers every aspect of the ocean systems, but usually conceptual feasible studies, then preliminary design, and after that you build a contract design. And if you want to have the competitive edges, you got to show something. Higher quality, we think suspension, airbag, and everything. Or in contract design, you got to show the delivery time is such and such. So in contract design, in order to show your competitive edges, well, you need something like this. After contract is awarded, detailed design or production engineering, manufacturing planning will be done. It is not 100% true, because it is make-to-order system. You're basically building brand new product every time, so it is darn hard to estimate your production time accurately. So some of this basic production engineering and manufacturing planning is done before in the contract design. However, these are just flow of these design phases. The bad thing is it is kind of trade-off analysis. Many departments, like reliability analysis team, structural shipbuilding, ship motion analysis, there are many specialist departments. However, you have to keep those kind of specialized department because it is your key knowledge bank. However, just keeping those kind of team, you will continuously suffer from this over-the-fence design. I think here are some students who are experienced in the mobile harbor design project, and some of the team are working on the mooring analysis, and some of the people are working on the axiomatic design of the overall system. But I guess their word and their presentation are totally different to each other. Axiomatic design just focusing on the requirement, design parameter and the like, but if you go into the mooring analysis team, they don't care about DP or FR. They are just calculating and calculating and calculating. But we need all these engineers to make our design project successful. It is best world-class practice, also known as Korean practice. Okay? Buyer side, ship owners or plant operator, they are not just a blinded customer. They know everything. And actually, many naval architects or marine engineers are hired by ship owners' company to do their own homework. So transportation economic studies, performance specification are already studied and researched and done in ship owner's side because it's a huge amount of investment. You cannot just go ahead and purchase that out of this ship. Okay? Shipbuilder side also have to do some kind of future forecast because it's a highly variable market. You got to keep your resources based on this need, highly variable. So got to know the market forecast. Also got to have your own design optimized to your production facility. Once again, this is a make-to-order system. Okay? So even though there are exactly identical container carrier, the detailed design of Daewoo Shipbuilding and detailed design of Samsung Shipbuilding will be different because their production facilities are different to each other. For example, if A shipyard has the erection crane capacity of 900 ton, and if B shipyard has, for example, 500 tons of erection crane, their block design, block division will be totally different. Okay? And version of design to meet customers' need and customer focused throughput. Those could be your kind of competitive edges to keep you alive. Okay? And this is quite interesting thing. Detailed design and production engineering are usually done by standard intermediate product design. For example, one of the Korean shipyard, even though they have different product to manufacture, it could be LNG carrier, it could be a crude oil carrier, container ship, or one of the semi-submersible oil rig, whatever it is. They try to extract the similarity between intermediate product, the part, basically blocks. The reason for that is they wanted to achieve the economies of scale, even though they build a totally unique intermediate product. Why is this similarity? The reason for this applying economies of scale, 규모의 경제, is to make your production more efficient. I mean, productivity level will raise if you do the same thing again and again and again. Even though we don't have any same thing, but we can extract the similarity and extract this high productivity level. Okay, any questions so far? Okay, this is the end of this marine design review. I mean, throughout this 6 very short slides, I just talk about the characteristic of our marine design compared to other automobile design, building design, and other things. Okay.